All right. So we're going to be doing probability and statistics. And today we're more going to be looking at what is the definition of probability. All right. So probability is the chance that something's going to happen. All right. We usually express that chance as a decimal, a fraction, or a percent. Usually almost always starts out as a fraction. It's the easiest way we can look at these. It's a fraction, obviously. We're looking at a number between 0 and 1. If something has a probability of exactly 0, in the first kind of extreme, that means it's never going to happen. You know, there's a 0 chance that a pig is going to be yellow, something like that. And then there might be a 1. A 1 is like 100%. So 100% chance that something's going to always happens. So if you take a look, if we have an experiment, we call these experiments or trials, and we have a set S of equally likely outcomes, and we'll get into what that means in a second. The probability of some event, which is one or more of those outcomes, is, we read this just like a function, probability of an event is the number of outcomes in our event divided by number of outcomes in our total set, and we call it total set our sample space. So if you got sample space is kind of the whole thing. Everything that's ever possible is in your sample space. Then you pick out which things do you care about. Those are in your event. Okay. You guys are going to have to get used to this this kind of new vocabulary, but you should already know some of these concepts from 9th grade. At least the basic ones. So we've got our totals, our sample space, and then our, what we call it, favorable or inner event. So take a look at the first problem. We want to know the probability of rolling a 5 on a standard die. Okay? Now remember our formula. Probability of an event, the number of outcomes in the event divided by the number in the sample space. The way I always like to start is by finding my sample space, finding my total, whatever total outcomes I'm going to look at. So here we have a standard die. What are the possible outcomes for rolling a standard die one time? Could have a 1, I could have a 2, could have a 3. Okay, that's my sample space, my set S. Okay. Of these outcomes in the sample space, which one is favorable to this experiment? Number 5. So to find the probability, remember we're using this formula. How many are favorable? 1 is favorable. How many total? There you go. Probability rolling a 5 on a die is 1/6. All right. What about the probability of not rolling a 5? How many? 5, 6. How'd you get that? Five, 6. We have 5 that 3, 4, 5. We have 5 numbers that aren't in there. Now, notice in this question, the only thing I changed is I put in not, right? We call that the complement of rolling a 5, probability of not rolling a 5. What do you notice about the probability of rolling a 5 and the probability of its complement? You add them, you get 100%. Probabilities, what the rule is, if the probability of all the outcomes better equal 1, or else you did something wrong. It's like having a percent not add up to 100. It's the same idea. But what that means, what we can use that rule, is we didn't have to do, I know this was a basic one, but we didn't have to look at this, write out all 6, and count that there are 5 things, not 5. We could have just done 1 minus 1/6 and gotten the same answer. And we're going to take advantage of it later when the problems get a little more complicated. All right. Everybody give this one a shot. Probability of rolling an even number. All right, what's somebody get? What was it? 3/6 or 1/2. I like the way you said it. Usually in probability, I like to always start with just the regular fraction where it's real straightforward and then reduce it. Don't try and reduce it right off the start, because when you start getting into other things, you're going to have to see a pattern. Like remember that one series question? It was easy to see the pattern if we kept the fractions, but if you reduced them, you kind of got lost. All right. Now we'll get into something a little bit different. Here you have 10 dowels. Does anybody know what a dowel is? What's a dowel? Yeah, long or short. They're they're like a coat rack. You make them in a coat rack. You got the pegs that you put out there. So we have 10 of these, each with diameter. They go from diameters of 0.5 inches to 5 inches, half-inch increments. Okay, so knowing that, who can give me my sample space? The sample space is not always numbers like on a die, don't forget. Sample space is the number, the things, describing the things, all the outcomes. .5 is the first. I'll write it on here, actually. My sample space, my set S. In this problem, it's going to be useful to go up by diameters. So you said the first one was 0.5. What's the next one? Then 1.5. Keep going. Yep. 4.5 and 5. These are a total number of outcomes. We have dowels with diameters ranging from 0.5 inches to 5 inches. Okay. We want to select one of these dowels. We want to know the probability it fits through a 2.1 inch diameter hole. Okay. So if I have a hole that's 2.1 inches and I have pegs ranging from 0.5 inches in diameter to 5 inch diameter, which ones are going to fit through a 2.1 inch diameter hole? Anything below what? Anything below 2. So which ones? Which one? Yeah. 1.5 and 2. 2 will fit through a 2.1 inch diameter hole. So what's the probability that one of these fit through? 4/10. Perfect. Or 0.4 or 40%. 2/5. Let's see what I write. All right. So sometimes when we're looking at our outcomes, they're not as obvious as they were in the last couple of examples. When this happens, it helps to write out and have like a flow to it. We use something called a tree diagram. Now this, unfortunately, is not, we're not able to draw these out in your calculator, so you have to get a separate sheet of paper in your notebook or something and do the tree diagrams out. All right. So here we want to draw a tree diagram to illustrate the sample space of a person having a bag with a red, a black, and a white ball in it. He's going to remove the balls one at a time without replacement. Okay, what does it mean without replacement? Anybody remember? Without putting it back. So if he pulls out the black one first, he's going to take the black one, he's going to put it on a table, he's going to reach with the other two and pull those out. So the way you're going to start these, you always start from the top. And then you have your possible outcomes. So what are your first possible outcomes here? What could happen? If I have a bag with 3 balls in it, what's one of the things that could happen? I could pull out a red one. What's another possible outcome? I could pull out the black one. What's another possible outcome? I could have pulled out the white one first. Okay, so the way this works, it kind of flows down. So now you're looking specifically. I pulled out the red one first. What could happen now? I could pull out the black one. What else could happen? Could pull out the white one. Let's say I did pull out the red one and then the black one. What's my next possible choice? Is there another possible outcome? No. That's the only ball left. What about here? If I pulled out the red one and then I pulled out the white one, what's my... It'd have to be the black one because it's without replacement. All right, go through, try and do for B and W, for black and white. So what we get for the black ball first? Could have had a red. We could have had a white. If we pulled out the black and then the red, would have had a white. If we pulled out the black and then the white, would have had a red. For the white, what do we get? Red, red. Okay, so the way we read these is, like I said, we just kind of flow down. One possible outcome would be red, black, white. You know, another possible outcome might be white, red, black. Okay, how many total outcomes do I have? 6. My sample space contains 6 elements. Yeah. And the way that, easy way to count them, just count the last kind of branch, the last thing on each of the branches. So like here, this branch goes there, the bottom ones, I have 6 of them. That means I have 6 different outcomes. Okay? Now they wanted to know what was the probability of getting a black ball second. How would I go about looking for that? So remember probability, we've got to have our number in our event divided by our number in the sample space. What's our number in the sample space? 6, okay. Number in the event. The event that we're talking about is a black ball second. How many of these have a black ball being pulled second? 2. If you look at this outcome, there's a black ball second, and this black ball second. So 2, 6. Red is a third, or 0.33333, whatever you want to do. All right. Everybody give it a shot real quick. Try and draw this tree diagram. Don't worry about the probability question yet. Just draw the tree diagram for a fair coin and then rolls a fair die. All right. Who can tell me how to start? Who can tell me how to start this? Start with the coin. So I'm going to start. Remember, you're always starting from one central point. I'm going to start with a coin flip. So how many outcomes are in the coin flip? Two. I could have a heads or a tails. Okay. Where do you want to go from here? What do you think? Where am I going to put? Right after the heads. So after the tails, I could have had a 1, a 2, a 3, a 4, a 5, and a 6 rolled. And after the tails, I could have rolled a 1, 2, 3, 4, 5, or 6. Okay, and they had a question with it. It said, find the probability for getting a tails and an even number. What's my total in my sample space? 12. I count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different outcomes in my sample space. How many outcomes are favorable to me? 3? 3. What'd you look for the 3? What was it? Tails, so you follow it. Tails. First outcome is tails, and then after that we have an even number. We could have gotten tails in this even number, tails in this even number, tails are this even number. 3/12. All right. So sometimes instead of using tree diagrams to count the event or the sample space or whatever, sometimes it breaks up in such a way we can use what's called the fundamental counting theorem. So this means what we're going to do is we're going to take our event and we're going to break it up into smaller events. You have to use all the smaller events have to come to the big event. And then you can just multiply the small event and you get the total in the big event. And that's what we have here. Number in the big event equals number in event sub 1 times number in event sub 2, all the way up to the number in event sub n. And I know that sounds like a lot of words and stuff, but it's really more straightforward than you would think. So take a look. Suppose for lunch you're able to choose between 3 types of pizza, 2 different fries, and 4 different sodas. Okay? How many different lunches can you order? So our big event is our lunches. What's one of the smaller events? Huh? Pizza. Perfect. How many different types of pizza are there? 3 types of pizza. That's our event 1. What's another event? Soda. How many different sodas? 4 different sodas. That's our event 2. What's our last event? Somebody in that table. Somebody in that table. What is it? It was quiet all day. It's our last event. Fries. How many fries? 2 different fries. I've got all my parts of my big event broken up into my small events. So I could just multiply these together. What do I get? 24. There are 24 distinct lunches. Okay. Everybody got this? All right. This one's a little different. Here we're going to have a locker requires a 6-letter code. And we get the code by rearranging the letters in the word Zaloom, okay? No letters can be repeated, but keep in mind that there's 2 O's in the name, okay? So there's going to be 2 O's. How many distinct locker locks can I make using that? So the way I start for this one, using the same thing. I know there's 6 letters, right? There's going to be 6 blanks. So what I do is I immediately write 6 blanks, okay? This is like, if you guys had in 9th grade the license plate problems, this is like those. So how many letters could I put in the first thing? What are my options? I could put any one of the 6 letters. I have no limitations or restrictions. What about for the next one? How many could I put? 5. Why 5? I already used one, and it says no repeating somewhere. Here, no letters can be repeated. So here I only have 5 options. What about the next one? Next one? 2, 1. What do I have to do with all these numbers to use the fundamental counting theorem and multiply? Okay. What was it? 720. So I can make 720 different locks. All right. So now remember I said license plate problems. Here's license. License plate has 4 letters and 3 numbers. How many license plates are able to be made if 0 cannot be the first or last, but the letters and numbers may be repeated? How many blanks am I going to put up? 7. All right. Go ahead and try it. All right, so let's take a look at this. We have 4 letters and 3 numbers. 0 can't be the first or the last. How many possibilities do I have for my first spot? 35. How'd you get 35? There are 26 letters in the alphabet. Now, just in general, how many numbers are we talking about here? What numbers are we talking about? We can put 0 to 9. So we're going to have 10 numbers. Yeah, you can't have double digit. You can't have 0 in the first one, so there are 26 total. 35. How many possibilities for the second one? 36. We can use every combination now. What about this one? What about the next one? 36. And what do I put in the last one? 35. Okay, so if I'm using the fundamental counting theorem, what do I have to do with these numbers? Multiply them together. What do they multiply to? Oh, you gotta go slower than that. Yeah, I think that's what we got in the first class. What do you got? Big number. Yeah, big number. What's the big number? Six zero. Anybody else get that one? So that's our total number of license plates. Now, for the last thing, this one isn't on here, I don't think. Yeah. Let's say I had the same thing, but now I say that it has to go 4 letters first, and then the 3 numbers. Okay, so the first 4 blanks have to be letters, the last 3 blanks have to be numbers. Do the same, find the same question, go on your own. While you're doing that, remember your homework is only going to be page 2 in the packet you just picked up. It's only 3 questions. All right, there is a review class tonight, linear relationships and functions. And what else? Oh, and you all should have gotten weekly project 22 in the new quarter 4 folder. Only page 2. All right, so real quick. So I got my 7 blanks. I have 4 letters and 3 numbers. How many possibilities can I put here? I can have the 26 different letters. What about here? 26 different letters. Keep going. 26 different letters. 26 different letters. Okay, after that, I'm going to have 3 numbers. How many numbers can I use as a possibility for here? 0 to 9, so 10 numbers. 0 to 9 is 10 numbers. Right? When can I use 0? Yeah. Can't be the first. That, yeah. Is this the first or the last? No, it's in the middle. How about here? 10. How about here? All right. So if you multiply those out, you get some number. I'll let you guys do that on your own. All right. Yep. All right, so that's going to be it for today. Remember, we got page 2.